Good morning, good afternoon, and good evening to all of you joining us from across the globe. I wouldn't be wrong if I said this. It is truly an international webinar because we have participants from several countries joining us today. So, welcome to this global session on practical power amplifier design using Keysight ADS. My name is Sharath, and I work as an account manager with Keysight Technologies, and I will be your moderator for today's session. Just a quick note before we begin. For those who have been following our webinar series, the Keysight webinar series, you will know that this session is part of our ongoing technical series focused on RF circuit design, RF system level design. A few weeks ago, we hosted a session on low noise amplifier design as well, LNA design. And today we are continuing that journey into a deep dive of power amplifier design using Keysight ADS. We will be continuing this series in the coming months as well. So covering more advanced RF and RF system level topics. So if you're enjoying these sessions, stay tuned. There's a lot more coming. So, all right. It's my pleasure to introduce our speaker today, someone who honestly needs no introduction, Mr. Anurag Bhargava. Anurag is a well respected name in the RF design community. Many of you already know him from his popular YouTube channel. All of you recognize this face, this name, this YouTube channel, where he shares a lot of practical design insights, tutorials, and Keysight tools based workflows that have helped engineers and students across the globe. What really stands out with Anurag is his ability to break down any complex topics. That's what I keep hearing from a lot of my customers. He makes these complex topics into something so simple and actionable. So a lot of customers appreciate that. So if you have already haven't checked out his channel, you can check that out later, YouTube at Anurag Bhargava. But today you will have the opportunity to learn live from him. So Anurag, over to you.
All right. Good morning, good afternoon, good evening from wherever you are joining. And welcome to today's webinar. It's a marathon webinar for approximately 2 hours, but in between we will have small breaks. We will look at question and answer. And considering the number of people who would be joining us today, it might not be possible to answer every question that we receive, but be assured that we will get back to you in case we cannot get to your specific question during the webinar. So let's begin this exciting journey of practical power amplifier design using Keysight ADS. My name is Anurag, as introduced by Sharath. I work as Customer Success Manager at Keysight. Over many past years, I have heard many people, whether it is about Keysight tool usage or whether it is all about learning how to do basic RF microwave designs ranging from passive to active. So today's session is focused on a pretty interesting topic which a lot of people want to learn, and it's about power amplifier design. So during next couple of hours, we will go through each of these topics in a little bit of detail. As you can see, we have a lot of coverage to do. So it may not be possible to get into very lower level details of each of these topics, because you can virtually think about any of these topics and you can easily discuss for 1 or 2 hours because everything is so involved. But hopefully at the end of the session, you will have sufficient information to go back and start doing things in a more appropriate manner without having to jump around, various places across various tools. So the key takeaway, which I would like to make sure all of you get towards the end of the event, is you will realize how indispensable ADS is for all your practical RF microwave design, and what sets ADS as a tool in its own class, which is unmatched in the industry. So I'll go through each of these topics, so stay tuned and feel free to type in any questions you may have in the Q&A panel, which you should see in your Teams window, and we will get to that at appropriate point. Now here, this is my take. Different people think, these kind of circuit design differently, but this is how I see it. So in case of any RF microwave circuit which you might be designing, and in this case, we are talking about power amplifier. If you think about optimum design life cycle, which kind of gives you assurance of minimal surprises when you go into a testing table, is covering these three main broad segments, if you will. So starting from the left, which is where you design circuits to meet your basic performance, and in case of power amplifier, you do analysis like one tone, two tone, and make sure all your frequency domain parameters are being met for the specification you are designing the amplifier for. Eventually, this amplifier or whatever circuit you are designing eventually goes to some application scenario where your circuit has to deal with various kind of modulation schemes. It could be commercial modulations like 5G, 4G, Wi-Fi, or it could be defense application where you might be working on satellite or radar and those kind of configurations. So every standard will have some sort of modulation. Nowadays, you don't see analog modulations too much. It will be likely having some kind of digital modulation. So depending upon what modulation techniques you're using, your circuit goes through, various changes, and that's what you need to ascertain. And if you're not simulating your circuits to validate how it behaves in a particular modulated condition, you might miss out something. And during testing only, if there is any issue, will be discovered. And by that time, it's already quite late. And then you will have to rework a lot of things. So that can cause project deadlines to be missed or unnecessary expenditure on your company and the time investment which you have to do. So eventually, once you validate that performance, at the end of the day, most of your circuits will not be used bare die or bare PCB level. So if you're doing IC design, the IC gets into some kind of packages. You might use bond wires or flip chip or those kind of configuration. So suddenly, from a single technology which you were dealing with, which is for IC, you end up seeing it as a multi-technology design because now you have some sort of mechanical enclosure, mechanical interconnects coming into the picture. Similarly, for PCB, the PCB you are designing eventually goes into some kind of box or a cavity. It could be a single box, it could be multi-cavity box, and so on. And if you have done RF microwave designs, you might have seen this is the place where you see a lot of surprises. The chip folks, when they measure on die performance, it comes out as excellent. As soon as they package and then test the package mounted on a PCB or something like that, the performance might change, even lead to oscillations. Exactly the same manner, if you design a PCB, test okay, but once you put in a cavity and things start to change a little bit. So then eventually, this is your operating model. This is how your design circuit will get housed. So you need to ensure that your circuit is working in a final assembly level situation. So as you can see, this is how thing progresses. But based on the specific design tool or the technology, sometimes we either don't have the tool or the knowledge know-how to make sure you simulate your circuit as much possible in the virtual world so that you have to do less struggle in the real world. And that's the whole intention of this webinar. We will go through this entire flow, make sure you understand that these things are not as complicated as we think they are to perform. And with Keysight tools, it's very, very easy to perform all these stages nice within your laptop or desktop, whatever you may be using. All right, so that sets the foundation. So let's begin. So before we begin, here are the modules I'm going to talk about. So just for your information, I'm going to talk about ADS, which is the core RF microwave package. So these are the modules which we will eventually go through, and this is what we will need to do complete design, whether it is simple S parameter simulation or doing layout, doing electromagnetic simulation, and the nonlinear or the modulated domain simulation. Then we are introducing two new packages, which is again to do modulation analysis and digital predistortion. Digital predistortion is very common in modern day power amplifiers to achieve the best compromise between linearity and output power and efficiency. And this is virtually applied with every power amplifier which is designed for real life application, right? So after the webinar, if you want to have an evaluation license, you would like to try out or you need further support, if you are in India, you can contact these three colleagues of mine. If you are located elsewhere, you can either write to support@keysight.com or you can request a free trial online by filling up a small form, and you will be granted evaluation license for 30 days. So at the end of webinar, you will have access to the slides I'm going to present. You will have access to the ADS workspace I'm going to present. But the ADS workspace will come without the transistor library, and I have all those instructions which you can follow to go and get the library for yourself if you want to use the same device. Or if you already have a library for a device, you can feel free to modify the workspace and use your own device, right? So you will have access to everything. The meeting is getting recorded. You will also have the meeting recording link to go and rewatch anything which you might have missed or you want to listen to that particular section again. All right, so let's start with something basic. Why do we need power amplifier? I hope everybody on the call already knows why we need power amplifier. Is the most crucial element in your transmitting chain to ensure that you are able to send your signal long enough based on the system which you are designing. So you need to have sufficient output power so that you can overcome challenge losses, right? So PA is the most crucial part in the transmitter to make it a transmitter. Without a PA, any transmitter is not really a transmitter for wireless communication. So in terms of design requirement, there are multiple requirements and often they are conflicting requirements. So first thing we need to remember, PA is the primary consumer of the power. So rest of the transmitter on one side, PA alone on one side, the power consumption is always equal, or in fact, sometimes power amplifiers consume more power than rest of the circuitry in the entire transmitter. So the major design requirement for a PA is how efficiently you can convert the available DC power to output power. And that gives you efficiency, which we often refer as power added efficiency. And this efficiency translates to either a lower operation cost if you're dealing with something like a base station where the electricity bill could be really high. And if you can make your power amplifier more efficient, you can save a lot of money, which you need to pay. Or in a handheld device, it could mean a longer battery life. More efficient your amplifier is, your battery can last longer. And who doesn't want their phones to work just 2 hours extra than what it is working right now, right? So these are very important things. Now, while you go for behind efficiency, PA linearity is another very important requirement because that determines how's your input versus output relationship. And you need your PA to be linear enough so that your signal integrity is ensured so that you don't end up producing so many distortions that the whole purpose of having a PA is canceled out because you end up generating so much distortion that virtually is useless. So a real design of PA at a 10,000 feet level involves a trade-off between efficiency and linearity. And these two are 180-degree opposite things. And as we go along, we will see how do we maintain both of these things with different techniques we have at disposal. Now, if you look at power amplifier, there are many classes of operation. Again, I'm sure a lot of you are already aware of this, so I will not go into detail. But just for the completion's sake, we have class A, which we know is high linearity and high gain. The output stage is always on. That means it's conducting for a whole 360 degrees. So you get very low efficiency due to that because you are burning DC power for the entire duration. And then you get overheating issues because you are consuming power for the entire cycle compared to what you are producing in RF output. Theoretically, you can reach efficiency of around 50%, but in reality, it's never more than 20-25%. That's the theoretical limit of 50%. Class B, that's where you only operate for half cycle. So you have less heating problem compared to class A, but you have less linearity compared to class A because then you have a clipping and then you will have crossover distortion problems to that. But in terms of efficiency, you can easily cross 78% or achieve in excess of 70%. Class AB, which is compromise between Class A and Class B. That means we conduct more than 180 degrees, but less than 360 degree. So somewhere in between. So Class A efficiency is 50% theoretical. Class B is around 78%. So in Class AB, practically you can achieve around 50 to 60%. You have better performance than either Class A or Class B because you have a higher efficiency. And this is one of the most practical amplifiers which most of the people design. It's a very widely used topology or configuration. And then you have Class C, where you have the highest efficiency of around 80%, but conduction angle is less than 180 degrees. So it's a highly switched kind of amplifier because of the distortions and the poorest linearity you can obtain in there. And then over the years, you have various other classes which have come up like class D, E, F, and now inverse F, and so on and so forth. So those are usually called as switched mode amplifiers because you almost operate at a very high level. So it's almost like a square wave, which is making your conduction angle 0. And theoretically, you can achieve 100% efficiency because you are almost operating like a switch. So you have a very less DC consumption, but everything you gain out of that is power in there. So that's a quick, refresher on amplifier classes. Now, if you want to learn more about different classes and how theory works behind the scenes, how you can emulate, my colleague Matt Ozales has put in various, videos explaining each of these. And I have provided the link to that playlist on this slide, where you can go and refer to Power Amplifier Basics, go over various classes. The best part about those videos is after you have watched the video, you have an option to request for the workspace he's using in the video. So once you submit your request, you will get a download link and you can download that workspace and practice on your own and then use that as one of the templates. So when I developed this class of power amplifier, I actually used a lot of his templates, which he did in this first video, which is on class AB, and that you will see in action in a few minutes from now. Also, while doing power amplifiers, most of you might have heard about stability factor. So the classic theory books teach us about Rowlett stability factor, and all those kind of techniques are only for small signal condition. In power amplifier, largely you are operating your device into a large signal mode. So a lot of those approximations are not valid. So you really need to do what we call as large signal stability. And in ADS, you get a very nice probe, which in short, we call it WS probe, but it's a Winslow probe. He's a research fellow. He's a fellow in MACOM, who has developed this flow in Keysight, and he collaborated, and we have his probe, implemented into Keysight. Now, how to use that flow, what all stability, conditions you have, again, in the same playlist, you have those videos there, and then it talks about various stability computation techniques, what's valid in what configuration, And at the end of the day, you understand how Winslow probe, one probe, can encompass all the stability computation which you have in the real world. So instead of you dissecting your circuits into 100 different ways to compute 100 different, kind of stability measurements, just one probe can help you do all those measurements in a very simple manner. So here is your resource. Now, again, coming to RF design tutorials, if you're new to RF designs or if you're new to ADS, as Sharath mentioned in the beginning, I do maintain a YouTube channel where I post multiple tutorials, starting from how to use ADS to how to do designs. With regards to power amplifier and the thing I'm going to talk about in this webinar, I have provided the link to this playlist, and these are the videos which you can refer to get more information on some of the topics which we will touch upon today, but we will not have time to go in detail, right? So two of the videos, which is 16 and 17, is going to give you much more detailed information about step-by-step power amplifier design, how to migrate from one step to another step, and so on and so forth. So that will be very handy. And then, of course, you can refer to other videos as well. Okay, so now let's begin our journey on power amplifier design. So where do we start? Any kind of nonlinear circuit design always starts from a nonlinear model. And it is essential, if you want to do a good design, you need to have a very good nonlinear device model. If that device model is not accurate, you will never be able to do an accurate circuit design, right? So garbage in is equal to garbage out, simple relationship. And depending upon whichever is your device vendor or the foundry you are going to work with, in case you are designing IC, it is their responsibility to give you a good nonlinear model, which is validated against measurements, so that you can have a good nonlinear model to start your nonlinear design. Now, there are various ways you can obtain that nonlinear model. Of course, the most preferred way is to have design kit for ADS, which is, in a way, you can call it library. So device vendor should give you ADS library, which contains their part. Most of the leading vendors already give you that kind of library, whether it is Corvo, whether it is Cree, or now Maycom, or any other NXP. A lot of those companies gives you design kit, which contains the model, and they are pretty good models. Right? Some companies, for some parts, may not be able to give you design kit, but they can always give you measured load pull data. Now, this is the easiest kind of data any nonlinear device manufacturer can give you, because most of them make these measurements within their office for every device category they produce. And once you have a measured load pull data, and if you are using the newer ADS releases, there is a very nice free utility which you can then load the data and convert it into what we call as artificial neural network model. We call it ANN. So you can take any measured load pull data, convert it to an ANN model, and now you have a pretty good nonlinear characteristics model, and you can virtually perform load pull, linear simulation, nonlinear simulation, every kind of simulation using that model. It's a new feature in ADS. So we recommend you to use ADS 2025 or higher version if you want to use that facility. Right? Of course, you can build your own nonlinear model. Keysight has another software called ICCAP. It is used by all leading manufacturers and foundries and companies to develop these nonlinear models. And there are some other alternate available. So the one I'm going to use in this particular presentation is from Maycom. It originally was from Cree. Then Cree was acquired by Wolfspeed, and now Wolfspeed is acquired by Maycom. So if you are not already a member of Maycom, you can follow this link, go to their portal, register yourself. Once you register and you get approved, then you get access to a download page from where you can download ADS design kit and then start using that component. So once I share you the workspace, this is the thing which will not be included because that model is usually given under non-disclosure agreements. So you need to register yourself and get these models, or use any other model. You don't need to be using only the model I'm going to talk about. You can use the model you have available with you. All right. So these days, most of the PAs are now shifting to GAN. In the past, it used to be LDMOS. You still have LDMOS there, but GAN is gaining a lot of traction in last few years. And one of the significant feature why people are switching to GAN is the higher power density. While the cost of GAN is still a little bit of concern in certain projects, but the advantages of GAN outweigh the cost barrier. So it allows you to generate more power in a small form factor. So you can work with a smaller device and you get much higher impedance. So since you have higher impedance, which is the inherent impedance of the device, your impedance matching becomes little easier as compared to LDMOS, right? And it can go to very high frequency as well compared to LDMOS. So if you are looking to do X band, KU band, those kind of designs, now you have GAN available, which goes up to that kind of frequency. And here is a comparison about the GAN material, or how does it weigh against other application or the need which you have there. So the device we are going to use is a GAN device. All right. So in order to create a tutorial, we need to have some kind of design specification. So here is a design specification that we will try to achieve. So we will be using MACOM gallium nitride 10-watt device, which is CGH 40010. It's an old device. It's not a new device. And now they even have the second generation, which they call it CG2H 40010. So either of those models can be used. So we will try to achieve, create 2.4 gigahertz as center frequency, bandwidth of plus minus 100 megahertz, output power, gain, return loss, power added efficiency, IP3, and thus the device, right? So with this goal in mind, we will begin our journey. Now, when you are doing PA design, and again here I'm focusing more on a PCB level PA design, the concepts apply everywhere, whether you're doing an IC design or a PCB design. But since PCB designers are in far greater number, we selected PCB as one of the topics or the technology to go through this tutorial, right? So how do you start? When you search for device, you find the device. Everything you should do is after a careful considerations of the data sheet. And I'll give you some quick guidelines, what to look in a data sheet, how to get a starting point before you begin your design, right? So look at efficiency of P out as they claim, make sure it matches your requirement. Small signal gain, it gives an idea what to expect during our design. Again, this may or may not be achievable depending upon what topology you end up using, what kind of power and efficiency you are gunning for, and sometimes you may or may not achieve exactly the gain which they mention in the data sheet. Every power transistor data sheet also gives you initial guidance of source and load impedance, and that was very handy because at the load pull is one of the most critical simulations that power amplifier designers need to perform. I mean, in a way, load pull as well as source pull. And that gives you an idea what impedance you need to present to this device to extract the desired output power or the efficiency which you are looking for, right? So getting initial guidance from the data sheet is very handy so that you don't need to do a lot of iterations and you can directly get to the point, right? Most of this data sheet also gives you a demo, board, circuit schematic, and layout that again may not exactly work one-to-one with your expectations, because they might be using some other dielectric, you might be using some other dielectric. And most of the demo boards, usually since it is for demonstrations, they do a very, very broadband kind of designs. In your actual applications, you don't need to do that kind of broadband design. If you need, then you have straight guidance, but usually you do much narrower band designs compared to how demo board is prepared. So in a way, from practical sense, that demo description which they have is an overkill, but at least you get an idea about topology, how to put things in your own PCB, and so on and so forth. So, but it gives you some reference. All right. So having said that, let's take a look at that data sheet. So here is the data sheet for CGH 40010. So you get an idea. Okay, it's valid up to 6 gigahertz. We are looking to do 2.4 gigahertz, so that check marks. Small signal gain around 2 gigahertz is 16 dB. And it also checks marks because we are looking to get gain of more than 10 dB. Pretty good. 65% efficiency at saturation, which is also good because we are looking at more than 50%. Right? And 13 watt as a P saturation, which is again good because we are looking at 10 watt output from this amplifier. So that's the initial checkpoint. Right? Now, after this, you can, of course, look at absolute maximum rating. And again, a typical guideline in RF microwave is whatever is absolute maximum rating given for any component, you should not ideally cross more than 50% of this. So it says your drain to source voltage, absolute maximum is 120 volt. You will try not to cross 60 volts because that ensures the life of your circuit. Because derating simply means more you work towards maximum ratings, the life of the product is going to go down. So I have seen some QAs which actually recommend not going more than 30% of absolute maximum rating. It all depends for what kind of life cycle you're designing a project for. If you're dealing with satellite, which has a life cycle of 10 years, you will take extra precaution. Remember, in satellite, once it is launched, it has gone. Even if something fails, you can't do anything for it, right? So you take extra precaution. If it is a ground unit, if it's a base station or something like that, maybe you can take a little more luxury. If something goes bad, you can go and still, go and change it or replace the part and so on and so forth. But this is a good thing to remember, absolute maximum rating. And this gives you a typical characteristics of the operating condition of the device. For example, here you can see VGS, which is gate to source voltage. Typical is minus 2.7. And that's the kind of threshold voltage, min, max, and so on. And the drain current, typical, and so on and so forth. Again, the drain efficiency. Now here, you have to make one distinction. There are two efficiencies which you will hear if you're dealing with PA. One is power added efficiency and another is drain efficiency. Now, if it was a live session, if I'm facing you, face to face, I will typically ask the attendees, which one you think is more practical? Should you go behind drain efficiency or should you go behind power added efficiency? What a typical specification mentioned? They simply can mention efficiency, but do they mean drain or do they mean power added efficiency? The answer to that is power added efficiency, because drain efficiency is simply the ratio of your DC power and output power. It doesn't take into consideration what's the input power. So you might be burning input power, but this calculation doesn't take that into account. Power added efficiency, however, take care of input power, output power, and the DC power consumption. So it's the right matrix to look for, right? So this one is not a right metric to look for, but for narrowband application, for simple application, this is good enough, drain efficiency. Okay, all right. So those are the two, critical pieces, or rather three. And now let's look at, okay, I need to design an amplifier. So what is this guy recommending? So always in the high power transistor, you will always find a section where it is giving you the optimum source, or not optimum rather, but the notional source and load impedance. And in this case, you can see we are operating around 2.5 gigahertz. And this is what manufacturer is saying, that you will find this device to exhibit around 3 minus J4 and the load impedance, there's a typo here. The load impedance is 19 plus J9. So if you are going to set up a load pool to find out which load I need to select to get the best output power, best efficiency, that's actually the start point for you. So when you set up your load pool template, that's the impedance you should start with. And then of course you will give a region in the Smith chart to vary and then see the device behavior over all those impedance points and so on. Right? Pretty important. If you go down, here is your bill of material for the demo board. Here is a demo board picture. You can see the transistor is mounted, and this is very typical you do in power amplifier because these are high power consumptions. So usually, even if you're creating a single PCB, you will create a slot in between and mount the device directly on the chassis or the mounting block, which could be of aluminum or any other material. So this gives you the instant kind of metallic sink below. And then behind this box or behind this mounting structure, you may have the heat sink and so on and so forth around that. Never mount a high power device on a PCB like you can do for LNA. You have this kind of device there. Okay. All right, going on, here is your sample circuit diagram. You can see here you have the RF input, RF output, you have gate and drain bias. You can see the decoupling capacitors, some placeholders. Wherever you see these R1, R2 as 0, that means they are placeholder. In case vendor or manufacturer has to fine tune this power amplifier for some other band or some other app, things, they can put certain components here and fine tune that. So these are just placeholders there. Okay. And you will also find this kind of topology, and I have received multiple questions of why people like to do something like this. Why is this RC? The simple answer to that is if you're designing a broadband amplifier, this kind of topology helps you, giving you more, stability and, flatter kind of response in a wider bandwidth when you put this RC network. Also, something very common in power cases, you see, even if you had a 0.5 picofarad capacitor, you will still put kind of two components in parallel. And this is simply because you have a high power output coming in. So you don't want one component to be facing the entire RF power which your amplifier is producing. So you kind of split them. Now, this has some side effect because now you will have higher parasitics and parallel mounting. So one good starting point to remember, whichever way you are going to assemble your power amplifier, you should simulate or you should plan like that from the very beginning. All right. So if you know you are going to mount two things in parallel, make sure in your circuit simulation, in your layout design, all these aspects are taken care of. Think of the destination, how the final product will be, and that is your starting point. Many times I have seen people start their design with a very idealistic things, everything is nicely connected. And then once they reach to a layout stage and they start doing EM simulation, EM circuit co-simulation, a lot of those things vary drastically. I've seen gain dropped from 15 dB to 5 dB. And then people scratch their head and trying to figure out what happened. Well, that's what happened. And I have a practical paper on that. So the link which I shared in the earlier slide about RF design tutorial, go and watch. There is a RF switch design example. That's a real case study done with a customer. And you will understand what are the implications of mounting these component parallel. So in your circuit design, you may be simulating it as maybe 2 picofarad, but now you are connecting them in parallel. This performance may not be equal to 2 picofarad and so on. That's what I'm trying to say, right? Now, purpose, somebody asked, I just saw a flash, what's the purpose of this R3? That RC is the low frequency stability. Every time you see a series resistor in a gate, path is for stability, especially at the low frequency stability, right? Now, Another thing to remember, uh, never leave any stone unturned to put as many decaps as you can when you're doing power amplifiers. Don't be too stringent. I will only place 2 or 3 bypass capacitors, because these power devices are very low impedance, kind of things. That means they have a high inductive content, or reactive content. So you would like to make sure that it sees the minimal amount of parasitics, because slight mismatch here, there, your device can go into oscillation, and instead of making a nice PA, you will end up making a nice oscillator. All right. So make sure you have enough bypass, you take care of all these parasitics and so on. So that kind of gives you a good guideline on how should you foresee. Now, based on your design application, your layout may look exactly opposite of what you are seeing here, but then at least you get an idea. Another thing, interesting thing, which you will also see in my design, is usually in RF microwave, we avoid putting short circuit stub. But this device is such that you cannot do a good output impedance matching if you don't do a short circuit stub, right? And here you can also see, even in the device manufacturer, they are using a short circuit stub here, right there. And that sometimes, unfortunately, due to device and its characteristics and its performance, you might need to use short circuit stub. So if you're RF microwave guy, be very careful whenever you see the short circuit stub. You need to ensure that you have sufficient via holes right at the point where you're short circuiting anything. So whether it is capacitor, notice here are the shunt capacitors, and you can notice one via hole right at the end of that capacitor, because you should not place these via holes far away from that component, because you don't want any inductive loop to get formed. As I said, these power devices are very sensitive, so you try to put as many via holes as you can. Plus, you should put these via holes as close to the ground point as possible. Wherever your component is connecting to ground, you should immediately see one or more via holes. There is nothing wrong in putting more via holes. It doesn't cause you any trouble. It actually benefits you in many ways. Okay, so those are some practical guidelines which is important to cover. Once you have an idea, you can get started with the PA design flow. And here I have ADS. And by the way, I haven't migrated my project to the latest ADS, which is 2026 version. So I'm still using 2025 update 2. But once you apply for trial, you will get the latest version available. So once I send you the workspace, or my colleagues send you the workspace, you will see folders like these. And there I have already mentioned it as part 1, part 2, part 3, part 4, so that you can go through step by step. Now, I'm not going to go through each of these steps. I have already covered some practical aspects which you won't find in theory books to cover, like how do you read the data sheet and what are the important considerations, which is going to help you. However, each of these steps are covered in a very great detail in the video link which I just mentioned, which is here. Practical power amplifier design part 1, part 2. Those are the key things for you to watch. Part 3, when I did, we used to have earlier way of doing modulated signal analysis. The reason I didn't mark it here, because now we have a much better and easier way to do DPD, to do modulated analysis, which is 10 times easier to use than what we used to have. Also, it is much faster compared to what we used to have. So whatever is covered in part 3 is still available. But in this webinar, I will show you the latest techniques which are available, which is of using Modulation Explorer and DPD Explorer. They are very, very easy to use. Virtually any designer without having any knowledge of wireless standard or digital signal processing can generate any signal immediately. And you can even get I and Q data from your digital folks or anybody whom you are working with. And those waveforms can be used seamlessly as well. All right. So let's go back to ADS. And so remember, I referred Matt Ozala's video on power amplifier basics. So I leveraged this as one of his template. I watched his video. I requested for the ADS workspace to be sent to me. And when I looked at it, I leveraged this schematic template. So here, as you can see, I have a MACOM transistor library loaded, and I'm using CGH 40010 part from there. And then it's a simple DC IV curve tracer. What's cool about Matt Ozala's workspace, once you typically run, in a traditional sense, you only see this IV characteristics of the transistor. And here you can see a classical gain characteristics where this gain seems to be falling off and so on, right? So what he did, he, based on his experience, because he is a previous power amplifier designer, he implemented some of these computation, which then you don't need to worry about how to compute transconductance, how to compute conduction angle, how to get an idea how much of power dissipation will happen depending upon your bias. And so this template is very interactive. And if I change my bias point, let's say in the class A mode, you can see the class A voltage and current. Red is voltage, blue is current, and this orange is your power dissipation. So here you can see conduction angle, duty cycle, efficiency. Remember, in class A, theoretically, you can get up to 50%. And here it is saying you are going. So this is only estimation, right? This may or may not be achievable, but this is what we can infer from the DCIV simulation. So large signal gain, excellent, because class A is known to give you more gain. So 23 dB. Output power to be around 36 dB. Again, based on your impedance matching, you can increase this number for sure, right? So once you start playing with this template, you can get a very quick idea of where exactly you should bias your device. So based on this template, usually GANs are operated at 28 volts. And here you can see with minus 2.7 volts, which is recommended in the data sheet, I can see the characteristics. So I'm going to get a small signal gain of around 15 dB, large signal gain of around 12 dB. Now somebody might ask, why are they different? Now again, we are not live, so it's not convenient to ask you, but if you know the answer, feel free to type it in the chat and score some brownie points, right? So this template you will get once I send you the workspace. You need more templates. Watch other videos from Matt Ozales, and he has excellent workspace with all these templates and equations. They are going to be very handy for a lot of work you're doing. All right, so once I finalize my bias, let's go to step number 2. The step number 2, in any RF microwave active design, unless you are making an oscillator, is to check whether this device is stable or not stable. That's what we call a stability analysis. And by the way, when you're just starting, you directly don't jump into doing nonlinear stability because this amplifier is still not seeing large signal condition. So first we need to stabilize this amplifier using classical stability equations, which are typically like Rowlett stability factor, which you call as K, or you can use mu and mu prime, that kind of configuration. So here, let me short this. So this is the bare device. I connected a controller and I'm running the simulation. And here you can see at the bottom, you have mu load and mu source. Both of them are less than 1. right? So that means your device is unstable. And based on this slider again, so right now this slider is kept at 2 point, close to 2.4 gigahertz. Here you can see load stability circle and source stability circle. So again, there are two concepts of stability. So once you are designing a particular circuit, you can choose to stabilize the device only around your frequency band of interest and don't care about what's happening in other frequencies. The second concept is where you like to stabilize the device in a broadband manner, depending upon the unity gain point, right? Which is typically what manufacturers will mention in datasheet. So if you decide to stabilize the device over a broadband, then your device becomes unconditionally stable. Once you're able to stabilize, that means no matter what source and load impedance you show the device over a Smith chart, your device will not go into unstable, condition. But if you're doing conditionally stable configuration, you need to be careful by taking care of these stability circles and make sure you don't show any source which is inside the circle. Otherwise, your device will see an oscillation, right? So choice is yours and so on. So with this, of course, the best way to induce the stability is to put some resistor in action. And if you're doing power amplifier, you will never put this resistor in the output side because there your output power is already pretty high and you are producing a gain after a lot of struggle. So by putting resistor, you will not like to eat away the gain you have, right? So typically you will find even in the data sheet I showed you, you found that they were using a resistor in series with gate and there was a shunt resistor with the gate bias. So right now we haven't done the gate bias design. So we're trying to see what happens if I put this 5 ohm there. And now once we simulate with 5 ohm, you can see now you have mu load and mu source greater than 1, you still have low frequency stability problem. But as you go along, you start to design the gate bias network, drain bias network. You can take care of this load stability, the lower frequency stability problems and all that. Now, when you're putting resistors, you also need to keep an eye on your gain, and you should not stabilize the device but achieve 2 dB gain. There's no fun, right? So you need to find compromising point between the available gain and the stability factor you have, right? So once you have stabilized the device, of course, you can go and perform load pull. Again, in ADS, if you look at design guide, you have a load pull, you have various templates available. So the one I typically start with is constant available source power, right? So once you have a load pull, you typically get this kind of template where you have a load pull instrument. And now you can define your bias condition, your frequency, and the impedance. Now, this is where looking at your data sheet comes in very handy because remember it had Z source and Z load information there, and taking a guidance from the data sheet, I put in the source. You see Z load center is 20 plus J0 and the source is 5 plus J0. So I took the guidance and I put in some number. I could put exactly the same, but near abouts is fine. So that is the region where this transistor is likely to give me the output power or efficiency I'm looking at. So once you perform load pull, there's a data display template that shows you contours of power and efficiency. And here, the art of PA is to look at a circle or the crossing of these circles where your desired PAE and desired output power are crossing. And for example, in this case, if I zoom in this case, it could be this point. If you show this impedance to your device, you can get the efficiency, which is given by this constant efficiency contour. and the output power, which is denoted by this constant output power contour. So look for those crossing points. And by the way, once you change your markers, these readouts will change, right? So here you can see the number is changing based on where you are placing the marker. This is a quick snapshot, which is ADS is doing a data mining and saying, if you present this load, you get this much of gain and you get this much of power at the output. Here is the power added efficiency. Now, if you want to select a load which gives you maximum efficiency, which you can see in this case is 65, that's the impedance you need to present. The gain will be reduced because, of course, your amplifier or device will be in compression, as you can see here, right? So more compressed your device, more efficiency you get because you are burning that much lesser DC power. And then this is the output power. So again, art of PA is choosing a compromising point where you get good enough efficiency and good enough output power, plus some delta margin to account for layout loss, component loss, SMA connector loss, and so on. So all those budgets should be in your mind, and you need to have that much of delta in here. So if you are looking to get 40 dBm output power, you should try to achieve like 41.5 dBm so that you have extra margin of 1.5 dB to take care of the transmission line loss, connector loss, and so on and so forth. Okay. If you gun for 40 dBm, once you go to layout, you mount everything, you put connector, you will be below the number which you are looking to design for. Okay, so enough said. And so you can follow those two videos. You can go through step by step. Eventually, it will go and talk about how to do impedance matching, how do you perform one tone, two tone kind of analysis. So here is the final amplifier design. Again, this is only at circuit level right now. And you could perform a two-tone third order, intercept point or two-tone third order IMD kind of performance. And you look at IMD here. So as per our specification, this should have been better than 45 dBc, and you are getting around 47. You have 2 dB of margin. So that's what you will achieve once you follow all the steps in the video. Again, for your reference, as you can see, I have step 1, step 2, step 3. So if you watch the video on one side, have access to workspace on the another, you can actually walk through and follow the video along. At any point of time, you can make modification suiting to your own requirement and be successful. But remember, this is just a general guideline of taking you through every step. By no means it's a gold standard PA design example, right? So don't treat it as such. Exercise your own cautions and checkpoints and balances and so on. Okay. All right. So once we have this final thing, whether we were able to achieve our performance or not, and the truth is when you do EM circuit co-simulation. So once you watch the series, you will go through various steps, how to design layout of this amplifier, what are the considerations you need to take in that amplifier, and you, again, keep end in mind and start and make the beginning. So always have, as I was saying earlier, you need to visualize how your layout should be. What is the available size you have? Do you have enough freedom to design your PA in 2" by 2", or you have 5" available, or you only have 1" available? So have all those constraints lined up and start back calculating, and keep that in mind when you're even doing a simple circuit level design and optimization. Okay. And again, your layout design. So there are various aspects. One is how good circuit design you do, how much practical things you take care. The second is how good layout design you do. Because if you give the same constraints to 5 people, all 5 of them might come up with 5 different layouts. All right. Now, depending upon how you route how you put things together, where you put the bend, how do you squeeze the size to minimum, will make an impact on your eventual RF performance. So doing this kind of EM circuit co-simulation is very, very crucial part, because when you do circuit simulations, it doesn't take care of parasitic coupling. Okay. So here, for example, this open circuit stub might be cross-coupling with this line edge. When you do circuit simulation, this coupling or coupling from this line to this line or this line to this ground, all these things are ignored. Right? They can only get captured when you do this kind of layout design. Also, many a times in the past, I have seen, although that trend is now slowly declining, people do circuit design in ADS and they didn't even realize that ADS can do layout design. And suddenly they moved out of ADS, they go to AutoCAD, they go to Eagle, KiCad, and whatnot, all those kind of PCB design software. After they do PCB design, they do Gerber export, then they do Gerber import in ADS and so on. Just remember, all those juggleries are not necessary. Once you buy even the most basic version of ADS, you have the layout already available to you. And that's a pretty powerful layout. So always try to do your RF circuit layout using ADS, because you can close this kind of loop and do EM circuit co-simulation, make changes on the fly, and re-perform EM simulation if necessary. So here what you're seeing is actually a virtual PCB assembly. Assume this PCB is fabricated and you mounted these component on that PCB. So this is reflecting a virtual PCB kind of assembly. So at this level, if you perform the same S parameter simulation, harmonic balance simulation, this result is closer to the reality, because it is accounting for layout radiation, cross coupling, interconnecting line transmission loss, impedance mismatch. Everything is accounted for here. So as you can imagine, remember we were at around 41.5 dBm earlier. Now with layout in place, your output power is around 40.5 dBm. And typically in gallium nitride, like in classical theory, we talk about 1 dB compression point. In gallium nitride, we talk about 3 dB compression point. That's why you see these two markers are 3 dB apart. So that's your input power at which you achieve 3 dB compression, which is 29.8 dBm. At 29.8 dBm, your 3 dB P out is 40.5 dBm. So you still have a little bit of margin, but this is little closer to what I would like to have. At this point, I would like to have 41 dBm, because remember, I still have two SMA connectors, which are not accounted for in this output power. And depending upon which connector vendor you use, you will have certain amount of loss, plus some extra margin for PCB fabrication errors and so on and so forth. Okay. So this ends the part one of this session, which is talking about the basic PA design knowledge, some practical tips, which you will never find in any textbook unless you burn your own hand or you burn at least 5 or 10 devices in your lab. All right. So and for rest of the step-by-step instruction, as I said, you can always go and watch these videos. Um, each of these three-part videos is 1 hour each. So they take you step by step into the entire design cycle. Okay, I think it's a good point to look at if there are some question and answers. So let me see, is there any Q&A? Okay. For Class A, Class AB, how to design the bias network so that it avoids DC current surge and against such. Okay, that's all about your basically choke design and the decap design. So it's a little more involved answer to give in this session, but hopefully you will find some references. Expecting design with other module with little high output power. I don't understand the question, unfortunately. Any tutorial available that shows conversion of measured load pull data into ANN? Yes, absolutely. There is a video available that shows you the example. We can later also send you a link. If you are a registered Keysight customer, you can go to our knowledge center and download the add-on which you can install in ADS and then watch the video of how to go about it, definitely. So my local team will get in touch with you, give that detail. Our DPD Explorer, Modulation Explorer included in the workspace to run core areas no, those are separate licenses. That's why in the beginning I mentioned the part number. So they are add-on licenses which you can add on top of the usual ADS design package. Will there be a recording link for the webinar? Yes, there will be recording link. The local team will share with you. Okay, so I don't see any other questions. Are there any other questions? That's
Yeah. Hi, Anurag, Pratik here. There were
yes, but
some questions in the chat window. I have compiled them. I will just ask them one by one. Is it okay with you?
yeah, maybe top three,
Okay.
whatever comes
Okay.
to you.
Okay. So the stability check from DC to 6 gigahertz or 0.5 to 6 gigahertz, which is important or correct if we are working in 2 to 3 gigahertz band.
Yeah. So as I said, both techniques are valid. Usually, if you ask me, I would first try to achieve broadband stability from 0.5 to 6 so that beyond that point, I don't need to worry too much about stability and what impedance I need to match. But of course, if device is very hard to stabilize, you can, of course, do whatever best you can. But in that case, I would say always keep an eye on source stability circle and load stability circle to make sure when you do load pull, you do not end up selecting a load or source impedance that is in that domain. Else your PA will go for oscillation. And for PA to oscillate, it doesn't need to be in your band. It can oscillate anywhere in any frequency till it has a gain of greater than 1. Okay. Right. Next.
Okay. Thank you. Yeah. So should we do load pull simulation after stabilization? Normally, after matching the impedances as per the load pull, we need to do tuning and optimization, and this will make our load to drift from the recommended load pull impedances. So
Yeah,
on that.
no. So load pull ideally should be done after stability matching. So there is no point doing load pull unless you have stabilized your device because you get pretty bad data anyways. Now, once you do load pull, you know the impedance which you, in ideal case, need to present to that device. So from that point on, all the effort which you put in to do impedance matching, network design, etc., should be targeting to achieve that impedance. The things will drift a little bit because all devices we work with are bilateral devices. But the recommendation I have here is remember our S12 is much lower than S21, right? S21 is gain, S12 usually is minus 30 to minus 40 dB for most devices. So always do output matching first and then do input matching. There will be a variance, but then the variance will be much lesser than if somebody will do input impedance matching first and then go for output matching, then the things will change drastically. But you can't avoid it, and that's why after you match everything, you do a fine tuning or final optimization to balance out the performance. That's how it should go. Okay, next. Last one maybe, and
So
then.
yeah. So this is one interesting question in the Q&A. Are there any kind of tips and tricks for multi-band PA tuning?
Not that I know of, but not something which is on top of my head, but I'm sure there might be some references available online. But it's art about, once you do multi-band tuning or matching, the whole thing is about what's your cue, which you need to cover. If the queue is very drastically apart or the points are very drastically apart, it becomes challenging. But as long as you are, I would say, in Q circle of 5, you should be reasonably okay. But anything more than 5, it might be challenging. So, but I don't have any more tips and tricks to share at this point. All right, so let's continue, and then we'll get to remaining questions in the next break, or depending upon how much time we have towards the end, or maybe after the webinar. Okay, so let's go. So, so we talked about only the PA design flow so far. So we talked about DCIV, stability, one tone, two tone, kind of things, layout design, EM circuit co-simulation. So once your that analysis, which is the basic one, right? There's no point going ahead if you don't even do the basic design. Now, after your basic design is done, if you remember my initial slide, now you need to think about application domain. You did a good PA design, but where is it going to be used? What kind of signals it is going to see in real life? Because one tone, two tone is good, right? One tone, good for initial characterization, two tone to reveal critical nonlinear behavior of your circuit, including your intermodulation, distortion, harmonics, asymmetric distortion, and so on. This is good. This used to be sufficient maybe 10 years ago or 5 years ago when we were dealing with nominal bandwidths of 2 megahertz, 5 megahertz, maximum 20 megahertz. With advent of 5G and now 6G is coming up, your bandwidths are increasing. So once you are dealing with 100 megahertz, 200 megahertz, 400 megahertz, in fact, now 1.5 gigahertz of bandwidth, you are not going to be very successful if you are doing this two-tone. Because what's the first rule of performing either two-tone simulation or measurements? These tones have to be close to each other. Ideally, not more than 1 megahertz apart. And then you predict what's happening there. So now that is the definition itself is for narrowband application. So if you deal with this kind of signal, which is wideband, not only wideband, it has a very high peak to average ratio. Look at all OFDM waveforms. They are very high to peak to average ratio. So your PAC is a very huge dynamic range, which it has to handle in the signal. So how about gain flatness? How will efficiency suffer? What about ACPR or ACLR? Because any communication standard, you're allowed to emit in your band, but you're not allowed to emit energy in the nearby or adjacent bands where somebody else might be operating on. So you have those restrictions to worry about. And then you have error vector magnitude, because now you have digital standard. So if you look at wider instantaneous bandwidth signals now, the way technology is moving now, you have very complex modulated signals and a very wide bandwidth, not to remember higher density modulation. So in the past, we were happy with QPSK. And now if you take a Wi-Fi 7 example, you have 4096 QAM signal. Imagine the modulation density and what kind of symbol to symbol spacing you have. So these kind of complex, denser modulation is giving you less and less freedom to do whatever you want. You have to be very precise, right? So that means one tone, two tone is not sufficient. And that's what basically this picture is depicting. So you have waveforms which have high peak to average ratio. You have envelopes which are widely swinging, right? They are non-constant envelopes. So when you deal with this kind of thing, if you're a PA designer, if you have to achieve linearity, what do? You apply back off. That means you operate away from your compression point. But then this brings to a problem because your efficiency takes a hit. Because depending on peak to average ratio, maybe at the peaks you are getting good efficiency, but at the mean level, you are getting a very bad efficiency because you are operating in a back off mode, meaning you are working away from the 1 dB or 3 dB compression point, right? With non-constant envelope, you have a wide dynamic range to take care of, and system becomes expensive, you have more complexity and so on and so forth. And if you don't take care of this, you will waste a lot of energy. You will shorten your battery life. You will reduce the range and signal transmission and so on. So side effects are too high when you are dealing with these modulated modern day signals. So what happens once you have this kind of signal going through your PA, you get distortion, right? That's what we saw in one tone, two tone, you see harmonics, two tone, third order, two tone, fifth order products, and so on. In modulation domain, you have two levels of distortion. One, the distortion which happens in band. So the metric which you will find in any communication standard is error vector magnitude. That measures the in-band distortion. How distorted is your signal in your desired bandwidth? And then you have a spectral regrowth, which is depicting out-of-band distortion, and that's what people refer as ACLR or ACPR, which is adjacent channel leakage ratio or adjacent channel power rejection and so on. Right? So these two becomes very, very important metrics, and you will find it in 4G, 5G, any kind of signal, WLAN, every modulation standard has these specifications. So if you test your PA on an instrument, this is how you will end up seeing your signal. You see the distortion in band, you see the spectral regrowth, see these shoulders. These are, if you want to loop back, these are two-tone third order kind of products, which is your one bandwidth offset. Then you have two-tone fifth order products, which are usually found at two bandwidth offsets on either side. And when you look at constellation, instead of your symbols being at ideal location, they kind of compress, right? So if you have AM to AM problem, they will compress towards the origin. If you have AM to PM problem, meaning due to input power, your phase is getting distorted, you will see a cyclic rotation of these guys. They will rotate in an angular fashion. So by looking at constellation, you can get an initial assessment whether you have amplitude compression problem or a phase compression problems and so on. Okay, so just to give you a picture, Wi-Fi is an example. So your EVM requirement gets more and more stringent with the denser modulation. So if you're working at 256 QAM, your system will say, give me EVM of less than minus 30 dB, which corresponds in percentage to around 3% approximately. If you look at 1204 QAM, because now symbols are much closer to each other, you have lesser dynamic range. Now you need EVM of better than 35 dB, even tighter specification. That means you need to achieve something like close to 2% or 1.5 or something percent. And then if you're dealing with 4096 QAM, which is at 8 to 11 BE, you need 38 dB. So life is not getting simpler because wider the bandwidth, more denser, more problematic it comes. So you can no longer, what it means to say, you can no longer rely on one tone, two tone test. You really need to do modulation analysis. Well, good in theory. So if I'm a circuit designer, I don't know what is 5G standard. I'm a power amplifier designer. I don't know what Wi-Fi says. I even don't know how to generate that signal and how do I simulate that signal. So if you're an amplifier designer, you need an efficient solution, which is accurate, and it should be very easy to use. And that's precisely why Keysight launched Modulation Explorer. Here is the part number. And the aim of this whole thing is to make it so simple that any PA designer can invoke this tool, generate the signal of his choice, run the simulation, and that's what you are going to see in next few minutes. Okay, it's pretty easy to use, and you can configure all standard signals which you see here. For anything which you have not listed here, you can always bring your own INQ waveform files. These waveform files could be generated from MATLAB. It could be operated from Simulink or from Instrument or any FPGA which your digital team is working at. So you can virtually take any INQ waveform file, define that, and put that INQ file. The format of that file is very simple, time versus I and time versus Q. You need just two files for that. And this tool, as you can see, step by step, you can go ahead, click on run, and then the whole performance runs. Now, after you run performance, what happens? Depending upon which standard you picked in, it will give you a compliance report data display. It tells you what all tests were done, whether your circuit passed or failed. And then later, once you scroll through the data display pages, you will see all these measurements automatically populated. You don't need to put anything in there. So instead of slides, let's get to the point. So here, for example, remember where did we stop? We stop at that point, right? This was the point where I have done all my one tone, two tone EM circuit co-simulation. That means my phase one of design is complete. I want to go to second phase. Now for Modulation Explorer, see, there is no source at the input. This only has a node called PA in. At the output, I have a node called PA out. That's it, because now Modulation Explorer will take control of the circuit. I only need to have maximum these bias supplies. Rest everything is as it is. Now, once I have the license and I have installed the explorers, and there is a separate installation available, our team can send you the link where you can download it from. Once you click on it, you get an option. You can open DPD Explorer, which I'm going to talk next. You can open Modulation Explorer, or you can open both. So for now, let's open Modulation Explorer. Click OK. Now it reads your circuit, and now it gives you a very simple GUI. At this point, you can actually minimize that. You don't need. So in block diagram, this is saying this is what I'm going to do. This is your DUT, which is power amplifier. This is the source which you can configure. You can choose to apply crest factor reduction, which is basically a technique to reduce peak to average ratio. And then I'm going to take your PA output and I'm going to do all related analysis. So at this point here, you can select either INQ file, or you can use any of these standards. In my case, I'm using 5GNR. You can define the bandwidth. Now, this is very simple for any RF power amplifier engineer. You define the carrier frequency and so on and so forth. Then to DUT, you see my input port is PA in node, output port is PA out, 50 ohm input, 50 ohm output. I would like to do this analysis. So without going into too many details, that's how simple it is. And now you just hit run. So when you're running, if you go to simulation control, and if you have switched on diagnostic mode, that shows you a complete step-by-step execution. So while this is working, let me go back to my slide. So you will get all these things in a moment. You will see that. And if you're working with uplink signal, let's say you are a handset or mobile manufacturer, then you are concerned with uplink signal. So exactly the same way it is available for uplink, WLAN, LTE, or whatever you want to do. Okay, so Modulation Explorer is already working. Now, exactly on the same format, we talk about DPD. Well, why do you need DPD first, right? So just now we talked about your linearity and efficiency are two conflicting things. If you go behind achieving higher efficiency, your linearity take a hit. Okay, so let's finish this first and then go to the next section. So after simulation is complete, you see this data display automatically opens, and now you have passed. Keep scrolling different pages. You can see the tabs at the bottom. You will see all these measurements were done automatically based on my power amplifier output. I in fact get ACPR. So my PA is giving me ACPR of minus 32 dBc on the lower side, and on upper side, that means upper sideband, minus 32. And it's passing right now, okay, because it's deal with the standard. And then you have out of band emissions, then you have waveform spectrum. You can see the red is input clean waveform. And due to PA operation, you can see the sideband has gone up very high. And that is why you are seeing ACPR of minus 32 dBc. Okay, and that's your CCDF. And then all the equations which are doing the magic. So as a power amplifier designer, you don't need to worry. Just pull up that box, define the source you want, just say run, and that's it. You get everything on your fingertips. Any more post-processing you want to do, of course, you are welcome to do most post-processing. Now from here, if you want to generate a PDF file to be sent to your customer or to your boss, just simply go to File, print all pages, and now in here you can define it to PDF, portrait or landscape, and you just say print. And let's say, let me put it on desktop and say 1, 2, 3, and you click OK. And now the PDF is generated, just send it as an attachment and your work is done. So you don't need to even do copy paste to PowerPoint and all that. It will give you a nice PDF with one page for each data display page. All right, so let's come to quickly to DPD. So you want to achieve higher DC to RF efficiency. That means you need to increase the dive level. With higher peak to, with higher peak power, you cause higher distortion because you are operating in a saturation. So to achieve higher spectral efficiency, meaning achieve linearity, you need to back off the drive level. And once you start backing off, let's say from this M4 marker towards this region, what happens? You see this efficiency, it goes down. Your linearity goes up. That means your ACPR will improve. Everything nice will happen, but just go. So how do we handle these conflicting requirements and still achieve our objective? Well, the trick is digital predistortion. It's a very popular cost-effective linearization technique. For a given power level, your DPD can improve EVM as well as ACLR. EVM gets improved because your linearity is getting improving. So your in-band distortion goes down. And since linearity is improving, your sideband performance also improves. So that also is a benefit. So what happens behind the scene? So this is how DPD concept works. Imagine you are linearly increasing the input power being fed to this PA. What happens to this PA? Of course, at the output, beyond a point, you start to see this gain compression, correct? And that's where we are operating at 3 dB compression or 1 dB compression or non. So in DPD, this characteristics is what we need to correct to make it follow this linear curve as much as possible, at least to our operating point. So the trick is, once you know the PA characteristics is compressing like that, you create an inverse characteristics, which we call as pre-distorted waveform. And this is what happens during DPD model extraction. It reads the PA characteristics, it creates a model which exhibit the reverse characteristics. So you don't feed this kind of waveform to PA in real world. You create an inverse logic, apply to that PA. PA works like that, and effectively they cancel out each other and you get a linearized response. That's the concept in the most simplistic term. All right, so that's how DPD works. But again, like everything, it has its own sweet spot. It works in a particular power range where linearity will be best improved. And beyond that, it will not improve. Below certain point, it will not improve. Once you know your PA operating point, you can always use different DPD strategies to do that. And also, if you are selling your PA to some other company, let's say in reality, I have many people talking to me who are power amplifier design houses. They don't do DPD design. But if they want to sell their product, they need to prove to their end customers saying, this is how linearizable is my PA. Here is the proof. So they use DPD Explorer in ADS just to prove that my PA is a good design, which you can then linearize later. Remember, depending upon how you do PA design, some design with the same device may not be able to linearize much. Even if you employ DPD, your ACPR or your EVM will not improve to the number you are expecting. Every design is different. Every topology is different. Every device is different. So whether you do DPD or not, sometimes you still need to do this analysis to prove that you have done an excellent design which will work in real world application. Now, how simple, how difficult? Very, very simple. Exactly like Modulation Explorer, you have this kind of user interface. You can choose your amplifier setting. You can generate your own modulation source, exactly the same types like what you can do in Modulation Explorer. You can apply different DPD model extraction mechanisms because sometimes you do DPD for mobile phone. Now in mobile phone, you cannot do the same thing that you can do with base station. So you have something like lookup table concept and so on. So depending upon your end product, you can choose various DPDs. Okay. And then finally do modulation analysis. If you are doing envelope tracking based amplifier, there is an option here. You can switch on envelope tracking, and then it will do more thorough DPD by tracking the envelope on which your PA is operating. So everything in a nice, GUI, easy to use. So let's take a quick look at DPD Explorer. So let me close this Modulation Explorer and let's go to our design. Again, same circuit bench. Go to here. And if I wanted to do both, I could have activated this option actually. All right. So let me show you. So if I added this option, now you have both capabilities and you can enable or disable DPD. If you disable DPD, you see, this is the picture you saw earlier in modulation analysis. And now this will work like a regular modulation explorer. And now if you enable, you see a few buttons added, this block diagram changes and so on. Again, concept is very simple. So before I explain, let me go ahead and simulate it because this takes a couple of minutes to finish. So you select what kind of signals you want to run, select input power, select your bandwidth and so on. Then in the DPD, you can use the DPD technology, which you want to use. So in the new ADS version, Keysight introduced a revolutionary model called dynamic gain model. This model can be extracted in ADS, or if you have a new generation PNA-X network analyzer from Keysight, that can also extract this dynamic gain model. So that's the great advantage of this kind of model. It's very nice, especially for Dorothy kind of configurations, which are highly nonlinear amplifiers. Dynamic gain gives you an excellent accuracy, which matches to very close to measurement. So that's step number 3. Oops. So by the time I could finish, DPD analysis finish, and you see the resulting data display. So let's first look at this spectrum here. So the blue spectrum is your native PA output, and that you can see your shoulders are very high. That is why you are getting 32 dBc ACPR. This orange or magenta spectrum is with correction. You can see the sidebands are significantly down, approximately by 20 dB or slightly more down there. Okay, so that's the DPD advantage. Suddenly you get a good linearity. You don't need to compromise. And here is a table you can compare. So when you had original signal being fed to PA, your peak power output was 40.2 dBm. Mean power was 32 dBm. When you apply DPD before PA, you get 41 dBm and you get almost the same mean power. Now, one might be wondering where output power has increased. Because in DPD, when you linearize the amplifier, let me go back to this slide here. Yep. So when you linearize this amplifier, you see now you will have much higher gain. That's called gain expansion due to DPD. So at the same operating point, you will get more output power because you are getting more gain from your power amplifier. And that's what you actually see here. You gain 0.8 dB of gain. So now I can breathe comfortably because now I have 1 dB extra to take care of my SMA connectors or any other manufacturing tolerance. Okay. So anyway, so just to quickly complete here. So again, you can go define your power amplifier. You can do what kind of analysis you want. Sometimes you only want to do ACPR calculation. Sometimes you want to do EVM only calculation and so on and so forth. Okay. So with EVM, you see, without DPD, at the PA output, you had minus 26 dB. With DPD, you get minus 46 dB. So that's almost 5%, 4.8%, and that's 0.5%. It's a 20 dB improvement in EVM. So now you have much lesser in-band distortion compared to the native PA, which you were operating on. Right? And what did you need to do to run these kind of analysis? Just configure this, run this, and that's it. So that's the great feature of Modulation and DPD Explorer that you have in ADS. All right, so at this point, we finished with second part of our session. We only have last part remaining, which is about, okay, I have done one-tone, two-tone, I have done my layout, I've done EM circuit co-simulation. I validated that my PA will work in a real-world modulation environment. How about assembly level? Because the PCB that I just simulated is not eventually what I'm going to measure in my lab. This PCB will put in a box, it will have a semiconductor. How about that? Will box give me some cavity effect? Will a semiconductor affect my performance? What will be the eventual final result? And that's what we are going to go there. But before we go, it's time for me to grab some water and maybe take 3 more questions, which I can answer. Pratik, you have top 3 questions.
Yes. So I think one of the thing is, does an asymmetry in IMD3 translate to asymmetry in ACPR?
Absolutely, yes. And that is called memory effects. Wherever you see that, that means your PA has memory problem, and you need to be careful with that. And when you are doing DPD or modulation analysis, that will be exhibited loud and clear to you.
Okay. So the next question is modulated signal analysis using VTB available for ADS version 2022 and above. Is there any alternative for that for the lower versions?
No, unfortunately. So for lower version of ADS, there's nothing available. VTB is virtual test bench. So in a way, what you just saw, Modulation Explorer and DPD Explorer, is the replacement for VTB because they are much more user-friendly, very easy to set up, much easier to run. One thing which I haven't shown you is inbuilt parameter sweeps. So you can do sweeps of power, bias voltage, temperature, and see how your signal behaves. All those features were very hard to do with VTB. So if you're using very old version of ADS, I would recommend you upgrade to the latest version of ADS, or at least get an evaluation copy, try it out, and then I think we'll be very happy with Modulation Explorer and DPD Explorer. Last.
Okay, the last question, I think this was very interesting. So does Modulation Explorer work well and fast for elaborated PA architectures? So certain PA architectures like class AB, inverted F, and Dorothy, you have talked about it. But how about two-way, three-way?
Sorry, two-way, three-way?
Yes. So that is something even.
I don't understand that question, so maybe we have to get back on that one because the question is not clear to me right now. But in terms of speed, I would say the Modulation Explorer and DPD Explorer are much faster. In one of the test cases we did for Dorothy configuration, the old VTB compared to Modulation Explorer was almost 9 times faster compared to some of the PA. But right now, both of them are available. If you feel more comfortable with VTB, go with VTB, but I would highly encourage you to look at Modulation Explorer and DPD Explorer.
Okay. There were many more questions, but yes, we can take it up offline. Thank you.
Oh, thank you. All right. So let's continue and let's talk about assembly. Now, I meet many designers who get amazed when I show this picture to them and I ask them, can you do this in ADS? can you do this kind of assembly in ADS? And 90% of them say no. They feel only third-party 3D electromagnetic tools, which are very popular in the market, only can do this kind of assembly. But at least from today onwards, just go with the impression that you could do all this without leaving ADS. And by being in ADS, you will reap all the advantages of the closed loop simulations that you can do. So you can do schematic layout, this kind of assembly. You can import these 3D enclosures from your mechanical CAD tool. If you're using things like ANSYS HFSS, you can get these kind of geometries from HFSS into ADS. If you use CST or any other tool, you can, of course, export SAT file and then use that into ADS. So there are multiple ways to do that, and everything nicely works under a single ecosystem without you having to leave ADS or do any export import to a third party. Because as soon as you export the layout or import something in ADS, you break the flow, right? So that's not the point. You are active circuit designer. Many a times you see the transistor will be involved, capacitor, resistor, etc. So those standard 3D EM tools cannot simulate active circuits, and that's the problem. Your main design platform is the ADS. As you saw, you have been taking a single device from DCIV all the way to finish the amplifier and perform modulation analysis. So it makes sense when you assemble this, if you want, under this assembly condition, you can do one tone, two tone, modulation explorer, DPD explorer. You can do all sort of analysis in a complete assembled mode so that there is no surprise when you end up assembling this inside, right? So ADS offers two main EM simulators. One is based on method of moments, which normally people call it 2.5D EM, which is very effective when you are doing only the PCB simulation. And we also have finite element method, which is commonly known as FEM, which is what you get in HFSS and those. So both of these engines are available and you can choose which one you want to use. Now, how to do that? Again, I had that link in my earlier slide where I was giving you a playlist link. I put it again here. Watch this tutorial and you will understand how to make assembly like this step by step. But since we have a few minutes left, I'm going to show you live and you will realize how simple it is to do something like this. So if you haven't tried it, go back and try. Okay. So let's take a live demo. How do I do this all assembly things and all that? All right. So let's go back and let me go to the layout of this PCB, which we were just analyzing. And that's where once you have the workspace, you go to part 4. In part 4, that's the layout, right? That's where you just saw EM circuit co-simulation. Now to assemble it into a box and things, I did only two minor changes to it. Number one is, you see, this is a traditional microstrip substrate where you have a cover at the bottom, which is infinite ground. And then you have a via hole, and this is your main signal layer, right? I made a change to here so that I have a finite ground at the bottom. All right, that's rule number one, not recommendation number one, actually, because remember in your PCB, if it's a 2-layer PCB, you have signal at the top, you have ground at the bottom. So this is simply replicating that. Okay, that's one change. The second change is, since you are going to do a 3D simulation, that means your dielectric has to be a finite size dielectric. So in ADS stack up editor, you have this concept called bounding area layer. So by default, you will have a stack up like this. And when that happens, you never know how big is this dielectric in X and Y direction. When you use any 3D tool, you actually draw the dielectric. In ADS, you're not drawing dielectric, you're only drawing the metal layers, right? So the way to define dielectric size is go here, bounding area layer, choose any layer which you have not used in your circuit design. And let's say in this case, I use bound layer. And now this substrate gets bounded by this layer. Okay, so once you make this change, pretty simple, you come back to your layout. Let me switch off everything and let me switch on bound layer. So here is my bound and let's switch off conductor. Do you see this rectangle? This is the size of the PCB. So this bound layer is used as a bounding in area layer. So now you have a finite dielectric size. Then this is your ground at the bottom, and then cond is your top signal layer. So that's exactly what I did, right? So once you have it, now let's go ahead and create RFPro. If you don't know or you never used RFPro, please go to my YouTube channel. I have 26 tutorials, very nicely explain how to use RFPro in a step-by-step manner. This is an excellent infrastructure to do your electromagnetic simulation in ADS. So I'm going to create a new RFPro view. I'm going to select the substrate that I just showed you. Click OK. And now somehow RFPro loves my second screen. So let it come up and I bring over to this screen here. Okay. So that's your layout. And you can get a live 3D view of the layout. Here is the dielectric. You can switch on dielectric. Now you can see a finite size dielectric. It's no longer that one. So that's your top conductor. That's your bottom, right? So how difficult it is to set up momentum or full 3D simulation. And if you have used other 3D tools, stay with me and you are going to get surprise here. Okay, so that's your top view. I can do full EM, and you see under options, simulator, I can choose momentum. I can choose full 3D FEM. Okay, either one. And now here is my circuit design. These are my components. I have few capacitors. You can see they get highlighted. And I have one resistor there. So these are defined as layout elements, but these are circuit components. So I can right click, change their role to circuit role. So now they become circuit component. You can see the icon is changed. I would like them to be part of my EM circuit co-simulation. So I will simply select them and add them into my analysis. As simple as that. Okay, I have these pins, as you can see, input, output, gate bias, drain bias. This is gate, VDS, and that's your gate for the device. Okay, so I have these many pins. You need to create a port. You first need to explain where is your ground, right? So this contour is going to be your ground. Simply define that. Hey, my reference is contour. And that's it. Now you can simply drag and drop. And now, bang, you created so many ports immediately. Okay. Now, if you want to choose wave port or waveguide port for input and output for full calibration and things, so you can open property editor. So this input is going to be TML, which is the waveguide port. Output is going to be TML. Rest everything I leave it to automatic to let software decide based on the placement location. So done. That's it. Your EM circuit co-simulation setup is done in less than a minute. Yeah. Now you just go to options, you define your frequency, choose, we already selected simulator, and you go ahead and run. Of course, I will not run it in live webinar, but once the simulation is complete, what I can do from here, of course, I can look at S parameter, etc., but I can generate a sub-circuit out of it. Okay, so I'm going to create a new cell, I'm going to create a sub-circuit. Now, what this sub-circuit has done already, see, it has your S parameter file. You have 14 port S parameter file. And remember, you had these capacitors for bias network, impedance matching, stability resistor. Everything is automatically connected to this block already. So only thing you got to do now is go to main ADS window, open a schematic to create a test bench, whatever you want to. And now from here, you simply drag and drop this symbol. You can see you have input, output, you have VGS, VDS, gate and drain for power amplifier, and you set up the simulation. And this is exactly what we have done here. So you see this bench, similar symbol. I slightly reoriented the terminals. And right now it is looking at a schematic. Schematic means it is your ideal kind of design, initial design. Run simulation. So you can see input, output, power, everything. So let's put a history. Then I perform FEM simulation. You can see with PA only. All right, which just I showed you. Let's simulate. And now you can see the comparison. See, towards the compression, now it is showing you lesser output power. And this is due to, you see, your impedance matching is getting disturbed. So that's your problem with your core simulation, that slightly the way you did things, the match is getting disturbed, so your gain is getting dropped, especially more in compression. So your PA is compressing much faster than what you were hoping. And if you want, you can take some corrective action. All right, so what about assembly? Hey, I need to do assembly, right? So let's go back to RFPro. Okay, this is where you had a setup. Now, if I have a cavity and box, you see in your ADS workspace, I have a spatial library here, which is a 3D component library. And I do have this EM Pro. Every time you buy a new ADS, you get EM Pro for free. And this EM Pro gives you 3D editing capability inside ADS. So in this EM Pro, you can draw your own 3D objects. You can import HFSS files. You can import any CAD file, any 3D CAD format. And then once you have it here, you assign material, and this can become ADS library. So this box here is a parametric box. See, if I change the box, for example, let's change the length to 80. And this is how I designed it. So now this box changes. So it's all parametric box, right? So once you have it, you can bring it here, insert EM Pro component, go to that library. Here's my box, insert, and here is your box. Okay, so now first I need to change the box dimension. So since it is parametric, I right click, choose the design parameter. I define the width as per my PA, which in this case is 40 millimeter. And then the length of this PA with some extra margin is around 51.6. So now I have a box of that size. Now I need to just place the PCB inside that box. So before that, for clarity purpose, I will shift this box slightly here and say done, right? So now box is slightly different. Now remember the way it is, you see there is a distance between this SMA pin to that surface. That's where your PCB gets mounted. Now, since it is my demo project and I keep changing my dielectric size to various levels, I have kept this surface to be parametric. And now I can go here. And once you have the ADS workspace, you actually will have this box. So in the surface height, I can adjust the surface height so that your PCB top surface is very well aligned to this SMA pin. So now you can see the surface has increased and now you have much lesser space there, right? So now I simply need to move this box, pick the center point of this surface here. Sometimes it can get tricky because I have SMA connector right there, but typically you pick the center snap point. And in here, you select the center snap point of this dielectric, boom. Simple, right? I bet this is not even this much easy in any other 3D tools you might have used. So now you have everything, box, PA. Now, how do you set up your PA analysis? Well, here, right click, create a new analysis. You don't need to disturb your earlier one. See, this box has SMA connector, it has its own ports, as you can see here, and I can create a port out of that. So now I'm feeding directly from here. So I no longer need this input pin of this PA, output pin of that PA, because now I'm simulating from one connector edge to another connector edge, right? Rest, simple. Here you have capacitor, inductor, resistor in this case. Nothing changes, exactly the same, except now my input port is here, output port is there. And then I need these ports, of course, right? Because you have a gate supply, gate, drain supply. So they will become part of this anyway. So now when you run FEM, it will include the box as well. When you generate a schematic, it will have box results included. So if I show you here in my test bench, I already have that. So here you will find there's another view, which is full PA with the box, exactly with the setting I just showed you. Click OK. And now if I run simulation, I'm accounting for box and SMA connector. Now you see, because of SMA connector and box, at the same level, your output is even lower. It was previously 39.5, if I remember correctly. Now it's 39.1. Okay, so now you are taking care of mechanical. Now, funny things happen when you have cover mounted on top of this box, isn't it? Because that's when the cavity gets formed. Right now, you're only accounting for SMA mismatch, SMA transition, this metallic boundary, but it's open air. So in the library I also have a cover plate model separately. And in here, box cover, insert OK. And now I have a box cover. Right? Same like earlier, I can go ahead and put this cover wherever I want and close the cover, run simulation. Now, RFPro has one another nice thing. Let's say you assembled everything first, but then later decide, okay, I would like to ignore this cover, or my cavity has a problem. I need to get an absorber to absorb the radiation. So EM Pro has a wide variety of materials available. So here you can see I even have an absorber, which is parametric. So if it comes to that your PCB or box cavity has a problem, you can even apply absorber. You can change the height of the absorber. You can change size of the absorber without leaving ADS at all. You can do this entire assembly. And if something goes wrong, if your circuit is heavily inductor capacitor dependent, once you are in your circuit domain, you can set up optimization because your box is not changing, your SMA connector is not changing. Those things are as it is. You can even optimize your design to mitigate the effect of SMA connector, box, cavity, etc., which gets formed. So again, refer to the video I mentioned. You will get a more detailed step-by-step instruction, but at least now you saw that from a transistor device all the way to full assembly simulation, modulation, DPD, everything is covered in your favorite tool, which is ADS. You don't need to leave ADS. And that's what sets ADS apart from any other commercial tool available. Most of them are point tools, or they force you to do export, import, does that. ADS is a very streamlined flow. Anything going wrong, you can always go back, fix it, and proceed with your design without having a need of export, import. So we have 2 minutes remaining in our session today. So with that, I put up this slide again. I will have chance to take maybe 3 more questions towards the end. But before we go to Q&A, remember these are the ADS packages we use today. So when you typically request evaluation license, you can request for most of the ADS modules. But if you don't do that, at least remember to ask for these part numbers in your evaluation license. If you are in India, these are the 3 guys you can contact with. They are your local contacts. And if you are joining from any other region apart from India, you can either send a mail to support@keysight.com or simply follow this link and request for your free trial online. So with that, thanks a lot for your attention. Good to have you. It was my pleasure to present you some of these. I hope you got some value out of it. You are going back with some new learning, which you can apply on your real designs, which you might be doing. Again, this is not the end. This is the beginning of our conversation. To make sure you keep Keysight busy, contact any of our local guys to help you out. With that, I will stop here and take last maybe couple of questions, and then we can close out the session.